I have to start with a correction from last hour. I said here lambda quarter, but accidentally I wrote here lambda 2 on the blackboard, on the board. So you have to correct it to lambda 4 here. I said lambda 4, just I wrote it the wrong way. The real problem of this antenna here is if the two dipoles are not perfectly matched to the impedance of these two transmission lines. If they are not perfectly matched to the impedance, this quarter wavelength here just inverts the impedance because this is a quarter wavelength transformer. And say if the dipoles are identical and they have, say, a standing wave ratio of 1 to 2, that's quite a good standing wave ratio for typical antenna. This standing wave ratio, because the equations are so similar, transforms immediately into axial ratio of the circular polarization. An axial ratio of 1 to 2 is a very bad circularly polarized antenna. So it's not, it's usually, typically is not a good solution because the impedances of the antennas are not very well matched. This hour I have to talk about something quite different, but still we are going to use the results of polarization also here. So if I'm considering my radio link, okay, if I have matching polarization, then the simple Friis equation applies. So if I have gain of the transmitting antenna, gain of the receiving antenna, the power in the receiver is the power of the transmitter times gain of the transmitting antenna, gain of the receiving antenna, lambda over 4 pi r squared, if this is r. And our polarization matching factor, we hope to keep this one at 1. So we hope to have things done correctly. But the problem is what we get besides the signal. Besides our useful signal, we may get into the receiving antenna, we may get interference from other users. Besides this interference that could be mitigated with other users, I also get internal noise. But also the receiver adds its own thermal noise. In radio communication, you are usually at relatively the lower end of the spectrum. And at the lower end of the spectrum, the noise of any resistor that's above absolute zero temperature, the noise of a resistor, say R1 here, R, just R, resistor R. The noise, if I filter it with, if my system has a finite bandwidth B, and this is a bandpass filter, already the antenna is a bandpass filter. What kind of noise do I get here if I have another resistor, another load resistor, the same load resistor here? Between these two resistors, I have power flow. And the power flowing in this direction, if the resistors are identical, power of noise 1 is equal to the bandwidth of the resistor, to the Boltzmann constant, and to the absolute temperature of the resistor 1. This one is at T1. I also have power flow in the opposite direction, because also this resistor may be at a temperature different, at a temperature T2 that's different from absolute zero. I have power noise 2 is equal to bandwidth times Boltzmann constant times temperature 2. This is, in electronics, this is also called Johnson or Johnson-Nyquist noise. noise in electronics, but it has a much broader physical background. The physical background is really the black body radiation, thermal radiation of the black body. Where does this hold, this equation? So this noise actually holds where the Rayleigh-Jeans approximation applies. Yeah, Rayleigh-Jeans and the Jeans approximation applies when the energy of the photon, Planck constant times frequency, is smaller than Boltzmann constant times temperature. So if I take room temperature T0 is equal to 290 degrees Kelvin, with Kelvin I should not write the symbol degrees, then this frequency, when this actually code, this frequency prime, or how do I call it, is around 6 terahertz. So the frequency should actually be lower than this corner frequency should be actually lower than 6 terahertz. And we actually have all radio communication below 6 terahertz. At 6 terahertz, the Earth's atmosphere, the air, is practically opaque. The loss at the insertion loss of the atmosphere at 6 terahertz is about 1 dB per meter, 1000 dB per kilometer. So forget any communication here. But the Rayleigh-Jeans approximation actually holds, and this was a long 100 years ago, or say 130 years ago to be correct. This was actually called by physicists the ultraviolet catastrophe. Why the ultraviolet catastrophe? Because if I increase the bandwidth of this filter here, I get here possibly infinite powers. And the power in the ultraviolet range of the light should be infinite. And that cannot hold true. So this was solved 120 years ago by Max Planck, by the Planck law of black body radiation. And the Planck law solves this by providing this limit. Above 6 terahertz, this thermal noise decreases much. But at low frequencies, this thermal noise is present, and in radio communication, we are going to work with this noise here. So what does our antenna actually do? Our antenna actually, let's say that we have a lossless antenna. Now I refer to the radiation efficiency with the letter eta. What does this lossless antenna see? In any body, it sees a resistor at a certain temperature. And this temperature, if the lobe of this antenna covers completely this resistor, I see this resistor here. So this will be actually my antenna temperature, the information about this antenna. So this antenna actually behaves as a resistor matched to the impedance of this antenna. That resistor R at temperature T8. This is an equivalent circuit. And this antenna will provide some noise power here, exactly in the same way resistors provide noise, radiate noise according to the Johnson-Nyquist noise. In the same way, the antenna provides this noise for the resistor it sees in the black body here. Why black body? Black body means that this black body has a reflectivity of 0. If the reflectivity of that black body was not 0, we could not see the resistor inside the body, but owing to reflections, we would see some other bodies being mirrored into this mirror and going back to the antenna. So if gamma, this was not a black body, if this were a mirror has a gamma of 1, absolute value of 1, we see other things reflecting in this black body, and we get the noise power of those bodies out of here. So since our receiver is going to use now a filter of bandwidth B, the actual noise power I get out of the antenna is now bandwidth times Boltzmann constant times temperature of the antenna. That's not the physical temperature of the antenna, because the antenna is a lossless device, so it cannot, lossless devices cannot radiate power, but the resistor, it actually sees in the black body. This also goes back to our discussion at the beginning of this course. At the beginning of this course, we were talking about the radiation resistor of the antenna. Antenna is lossless, but if I connect here a transmitter, power is being lost into space somewhere. Where? On a black body target. And that power of the transmitter is dissipated really in this resistor here, not inside the antenna. That's an explanation for the radiation resistance of a particular antenna. So these things also works in the other way around. It explains us things we introduced in the hard way 1 month and a half or 2 months ago. Now we see where that things come from 2 months ago. The radiation resistance is exactly actually to this resistor transformed by a lossless transformer, this is a lossless transformer, into a mode on a waveguide. A waveguide or whatever transmission line we have between the receiver and the antenna. What are the conclusions here? The Rayleigh genes, we talk about the spectral brightness. Spectral brightness, according to Planck Law, the complete equation for the spectral brightness is twice Planck constant, frequency to the third power over speed of light to the second power, 1 over exponent function e to the hf over kbt minus 1. This is the complete Planck law, and you see the Planck law, when this exponent becomes larger than 1, the radiation, the spectral brightness goes down very quickly. The spectral brightness is defined by the amount of power per unit spectrum, per solid angle of radiation, per area of this object here, spectral brightness. This is the complete Planck law, but we talk about Rayleigh genes. Rayleigh genes. Approximation. The Rayleigh genes approximation gives this spectral brightness as 2 times kb t over lambda squared. Now, our antenna has a single polarization. So with a single polarization, I only receive half of the power, because this power is always radiated on both polarizations according to the black body radiation law. Also this power, and you see the factor 2 here, and this 2 actually goes away. So this power, if I try to calculate here things, how does this thing, if I integrate this spectral brightness, how does this thing integrate? I should integrate it over the radiation pattern of this antenna. This thing, actually, what I get out of here is bandwidth of my receiver times Boltzmann constant, and the Boltzmann constant is approximately 1.38 times 10 to the minus 32 joules per Kelvin. This is an approximate value. After 2019, the Boltzmann constant is actually a selected value. It has some more decimals, but it's a selective value, and it's used to define the unit Kelvin. So that's just from the measurement. Right? This temperature of antenna is actually what the antenna sees over the 4 pi solid angle in all directions. Here I have temperature of theta and phi, what the antenna sees, multiplied by the power radiation pattern, so f of theta phi squared, d omega and below I have it normalized on the power radiation pattern. So this antenna temperature here is just the average what the antenna sees with its direction pattern. So this expression here is just the equivalent antenna temperature we have here. And now what do we actually see with an antenna? We see at the average weighted by its power radiation pattern. With noise, let's say immediately, noise is a completely random signal. With random signals that have no periodic variation, we actually sum the powers. Because if we consider this noise as a sum of phasors, but these phasors have completely random phases, so we actually sum the powers. And what we are doing here? We sum the temperatures, or in the final instance, the powers, if I would move this b times kb, if I would move them under the integral down here. So we always, with noises, because noises are random signals, we always sum powers to calculate. Now, what does the antenna see actually? Let's draw here an example. An antenna. And what does the antenna see actually to get the temperature of the antenna? We are only considering lossless antennas, pure transformers. The most simple target is just vegetation. Pine trees make good microwave absorbers, so they have gamma of 0 here. They are black bodies at microwave frequencies with actually the temperature that's quite close to 290 Kelvin. So this is the most simple target I may have. What falls into my radiation pattern of my antenna. Other things that may fall here, I may have ground. Ground is, yes, at around 290 Kelvin. But the reflectivity of soil is far from 0, so it's not 0 reflection. Actually, the most difficult thing to consider is a lake or sea. Lake has a gamma very close to 1. Its temperature doesn't matter because there are other sources that will actually be reflected in a water surface to get into our antenna. Like we have many strong sources in the sky. The sun is something very hot at radio frequencies. The sun in the optical frequency range is 6,000 Kelvin. But it's around 1 million Kelvin in the radio range. So the sun may interfere directly with our reception and may be reflected off the surface of the lake and also get inside me. The sun in the radio range, say if I say frequency around 1 gigahertz, it's the temperature around 1 million Kelvin. In these days, it's much more than that. In these days, we have very high sun activity, very large sunspots on the surface of the sun, and those sunspots radiate maybe 10 times this amount of those, so maybe 10 million Kelvin today. Because it depends from day to day, it changes the sun activity, radiation changes from day to day. On the other hand, we have cold sky. That may have a much lower temperature, a temperature of just 10 Kelvin. 10 Kelvin, where does this 10 Kelvin come from? This 3 Kelvin, or more exactly to be 2.7 Kelvin, come from 14 billion years ago when some foolish man detonated the universe and then the universe started. So it comes from the Big Bang. Other sources here are tiny stars that may add a few Kelvin, and also some scattering the atmosphere also adds something. In fact, this sky noise is not a simple frequency. Sky noise, if I draw it here, if I have frequency down here, say we start with 10 megahertz, I draw a logarithmic scale, 100 megahertz, 1 gigahertz, 10 gigahertz, 100 gigahertz, 1 terahertz. Say to end up with radio waves, what happens with the noise temperature of the sky here? Again, logarithmic scale for the noise temperature of the sky. This noise is pretty low in this range, between 1 gigahertz and 10 gigahertz. Here we are around 10 Kelvin. And this is actually the most valuable part of the spectrum, since we have little natural noise. This thing will go at 100 megahertz. It will go to around 1000 Kelvin, and it may go up to 100,000 Kelvin, 10 to the 5th Kelvin, at 10 megahertz, and this is actually the galactic noise. In our galaxy, also in other galaxies we have the same, but our galaxy is far the closest one. We have several sources that do not radiate as a thermal black body. They radiate much more at lower frequencies. So we have very high noise values below 1 gigahertz. What happens above 10 gigahertz? I have resonances of various gases forming the atmosphere. So I have here around 290 Kelvin because of atmospheric absorption. Where the first peak is at 22 gigahertz. This is water vapor. So water, H2O, and has about minus 0.2 dB per kilometer. But already at 60 gigahertz, I have oxygen, the oxygen molecule, because ozone has a different absorption. And this one is 14 dB per kilometer. I still have some values, but mainly with the noise, I also get noise radiating by the atmosphere. The atmosphere is also opaque here. Also, on the lower frequency here, the ionosphere is opaque, so it also doesn't let radio waves go through. So the most valuable part of the spectrum is actually between 1 gigahertz and 10 gigahertz, when the atmosphere is practically transparent, and I can make any kind of space communications over here. You can go to some little values you have here, like this valley here at around 40 gigahertz after the water vapor peak. This valley is actually used by Starlink, by the satellite internet. It's not as deep as here, but bandwidth was available, and so they put up here internet access. So this is what happens about noise. Let's see now what happens in our receiver. I have my antenna that has a certain noise temperature, TA. But now from this antenna I go into an amplifier, and amplifier also adds noise. So I have noise here, and I have noise here. The amplifier also adds some thermal noise. How much depends on the type of the amplifier. Usually the amplifier, and after the amplifier I have in my receiver some filter to limit the bandwidth of this noise, and I have to hear some signal to noise ratio. The bandwidth B. So I have the signal power here coming in, and the signal power here is amplified to PS prime is equal to PS times the gain of my amplifier. But besides the gain of the amplifier, I also have noise power. And noise power at the output that will play a role in this ratio, signal to noise ratio. That's all what matters in communication. The noise power will be gain times the noise from the antenna. The gain times bandwidth times Boltzmann constant times T antenna. Okay, that comes from the antenna. This receiver here, I calculate the noise of the receiver on its inputs. So this is temperature of the receiver. So I express the receiver noise on its input connection, so to be easy to calculate things. So plus temperature of the receiver. This noise power actually does not happen on the input of the receiver. It only happens on the output. I can only see on the output of the receiver. But in order to make calculations simple, and also because this gain may change, but it's the same with the signal and the noise. So because this gain may be quite large and may be variable, it's much easier to recalculate this receiver noise on its receiver input terminals. And this is also quite a stable parameter, so it makes sense to express the noise on the input of the receiver. So my signal to noise ratio at the output is now what? Signal to noise ratio at the output is now, here I have power of signal at the input times gain of the amplifier, bandwidth, Boltzmann constant, temperature coming from the antenna, noise coming from antenna, and noise coming from the receiver. You see here that this equation was on purpose written in such a way that the gain of the receiver cancels out. That's the reason why we recalculated the noise of the receiver. We found an equivalent noise temperature on the input, but this noise is not present on the input. This noise is added inside the receiver. And we can make the whole calculation of our receiver, getting the signal to noise ratio, and that's what we are actually interested in our receiver. Now, clever people do it this way. But science says that there are many more stupid people around than there are clever people around. So stupid people use stupid units for noise. And now we shall describe what with stupid units they mean. Stupid people invented a ratio called noise figure. Noise figure. And this noise figure F is defined as the ratio at which the signal to noise ratio degrades. So I take signal to noise ratio at the output divided by the signal to noise ratio at the input. In linear units, you see that this noise figure is always larger than 1 because the receiver degrades the story. If I rewrite this equation here, at the input, I just have signal power divided by Boltzmann constant times temperature of the antenna, times bandwidth. And at the output, I have these two values up here. So I have signal power times gain, and I have gain times bandwidth times Boltzmann constant times TA plus T receiver. And they invented this unit as the measure. This unit measures how much does the signal to noise ratio degrade because of our receiver. So this unit is actually a property here. This F is actually a property of my receiver. Is it really a property of my receiver? No, it is wrong. Okay, the signal power cancels out here. The gain cancels out here. The Boltzmann constant cancels out here. And the bandwidth cancels out here. What remains out of our expression? This goes up. So from my expression, now what I get here is now what the noise figure is. The noise figure is, I have, to remove this double fraction, I have TA plus T receiver in the denominator. And I have T of antenna in a double fraction goes up T antenna here. Or if I cancel out, if I try to solve this fraction here, what do I get out? If this was input, this is output. Yes, I get here, if I divide by the T antenna here, what comes out? Signal to noise out, signal to noise in. And how does this degrade? I get something like this. I can write this 1 plus, this is something strange I'm getting here. So, yes, I wrote it in the wrong way. Sorry for the mistake. It's actually the degradation. If f is larger than 1, then the signal to noise ratio at the output is worse than at the input. I screwed up this here. So I have to take this to the -1. This is my mistake I made. And I have to flip this ratio here. Just I messed up with this stupid. So if it's to the -1 is T antenna plus T receiver over T antenna. Okay, this is larger than 1. This is fine. We degraded our signal to noise ratio because the output signal to noise ratio is worse than the input signal to noise ratio. This signal to noise ratio of the output is smaller than the signal to noise ratio of the input. I mixed up input and output here. Okay, if I cancel out now, the first part of the fraction cancels to 1 plus T receiver divided by T antenna. This is now the famous noise figure, frequently in logarithmic units, f in dB. Now this is a power ratio, so it's 10 times a logarithm to the base of 10 of this fraction here, 1 plus T receiver divided by T antenna. And now people describe the performance of my receiver with the noise figure. What is wrong here? What is wrong in this expression? This should be a parameter of my receiver. But this expression actually includes the temperature of the antenna. The antenna is not part of the receiver, it's a separate thing. Antenna is one item and a receiver is another item completely independent of the antenna. So this is stupid. Only idiots can say that. But this is described in many textbooks as being the only true thing. This is stupid. It does not work that way. So what is a more sensible definition of the noise figure? We have now, the noise figure is very popular, especially about people that like to talk about decibels and that don't know what the decibels are. But you know, big mouth, no brain, always talks in decibels. We have to find a sensible definition. And the sensible definition of the noise figure is this one. Noise figure is now 1 plus temperature of the receiver. This is information about my receiver. Divided by a reference temperature. And this is agreed to be, this reference temperature is agreed to be exactly 290 Kelvin. That's room temperature. But we agree to this value. And then we have a unique relationship, or in logarithmic units, we have a unique relationship between the noise figure is now 10 times logarithm to the base of 10. Here of this expression 1 plus T antenna divided by T0 now. Not not antenna, T receiver. Now I'm screwing up everything here. T receiver divided by T0. How does this expression come around? It's all history. This expression, when it was used about 60 or 70 years ago in the middle of the 20th century, where this expression was actually used for two different things. Expression was used for cable communication and expression for use for terrestrial microwave links. In terrestrial microwave links, the antenna looks at trees. So it's 290 Kelvin. And in cables, loss actually happens in cables. Cables radiate as black bodies, again, at 290 Kelvin. This was perfectly correct in the middle of the 20th century. This thing became stupid as soon as the first artificial satellite was launched. Because if we point our antenna to the satellite, usually the satellite has cold sky as the background. And cold sky is much colder, so calculations become much different. Noise figure is not a particularly good unit. It's much better to calculate things with temperature as we did up here. So this is the explanation, but you will find this in books. In fact, now it does not make sense to have two different units, noise figure and receiver, and clever people usually just use a graph that relates both things. You have a copy here of this graph, just that relates, please distribute it around. You just have a graph that relates noise temperature of the receiver to its noise figure, related all to the agreed value of 290 Kelvin. And this is a very simple way to get around this noise figure and simply calculate things with noise temperatures when we know that we are always in the right way. How much noise do we get here? Let's try to make a calculation. How much noise do we have? Only this just to end up this hour, 5 minutes. Let's find a simple example. A simple example. This example here, a mobile phone. A GSM phone has a bandwidth of one GSM channel is 200 kilohertz wide. That's already a data. And the GSM phone has a noise figure of around 3 dB. 3 dB is just a factor of 2 here. A factor of 2 means that the temperature of the receiver is around 290 Kelvin. If I have this receiver inside this room here, I have all around, I have targets at room temperature. So in the room, the temperature of the antenna, if I use it indoors, the temperature of the antenna will be around 209 Kelvin indoor. If I go with the receiver outdoor, the receiver outdoor will see half the sky at 10 Kelvin and half the soil and 290 Kelvin. So in outdoor will be about the average of these two about outdoor. Because I see the half the antenna pattern, the antenna is omnidirectional on the phone, half of the pattern sees the sky and half of the pattern sees noise. Now if I make the calculation here, so the noise power here, now its bandwidth is 2 times 10 to the 5th power of hertz, times Boltzmann constant is 138 times 10 to the minus 23 watt seconds per Kelvin, this is joules, times temperature. Indoor I have 290 twice. So I have 580 Kelvin if I'm indoor. And now I can make the calculation. How much power do I get into this? So 290 times 138 is about 410 to the minus 23. So this is about 2 times 10 to the 5th hertz times, here we said 400 by 280, so 4 times 10 to the minus 23 watt seconds per Kelvin, times, here I stay with 2 kelvins because it was just 2 times 90. So 2 times 4 times 2 is 16, 21, minus 21 here because it was 400. Now it's 16 times 21 minus 5 is 10 to the minus 16 watts. Watts, because seconds cancels out, Kelvin cancels out. So this is 1.6 to 10 to the minus 15 watts. We need a signal-to-noise ratio of around 10 in order for the GSM-phone to work. Larger than 10, larger or equal to 10. So the minimum received power, the signal power should be larger than the per signal minimum, P signal minimum, and this is actually 10 times this value, 1.6 to 10 to the minus 14 watts. Now we frequently express watts in dBm, so P signal in dBm is 10 times logarithm to the base of 10, our P signal divided by 1 milliwatt. 1 milliwatt is 10 to the minus 13, so I stay with 10 to the minus 11 here. That's minus 110 dB. 1.6 is a factor of 2, is minus 1.6 is around 2 dB, is 108 dB, dBm, if I calculate this thing out. So that's the actual sensitivity of my receiver for the given data. How about the sun? That's a very hot, a very bright thing. Very hot, 1 million Kelvin. It is not that difficult with the sun. Because fortunately our antennas do not have much gain. And the sun only covers a very small fraction of our antenna. So if I draw the sun here, and if I have my antenna here, the beam of this antenna is usually much broader than the sun. So the beam of the antenna is very broad compared to the very small angle. So I have to redraw the sun here in the center of the beam. If I put the antenna to the sun, this is a very small angle of the sun here. So this alpha for the sun is just about half of a degree, or say 9 milliradians. 9 milliradians. This is very small. If I calculate things out for a gain of around 20 dB here, of some 20 dB, I get here a difference in temperature when I turn the antenna to the sun just to something around 480 Kelvin. 480 Kelvin from the total value for the sun that was 1 million Kelvin. Here I had 1 million Kelvin. In these days even more. I just only get a temperature difference of 480 Kelvin because this angle is much smaller than the pattern of my antenna. A little bit short, but that's it for today. Because I have to go up. There's some people that want the midterm over email. I have to send it over the email and bring down the the midterms here.